right, we're going to take just a few more notes here, just a little bit more, and you'll be done and ready for class next time. All right, so let's go to this question right here. You filled out the table above on the last video. So let's see if we can now answer similar questions about our other examples. So are having a data display and having an equation mutually exclusive? So if you go back to our previous page in our packet, you should see either your Venn diagram or this table that we filled out. Well, we're having a equation and data display mutually exclusive. No, they weren't, because there was an overlap, right? There was 7% of all pages had both. So definitely they're not mutually exclusive. Okay? No, some pages have both. All right, then it asks, are having a data display and having an equation independent? Support our answer mathematically. Well, if we go back and look at the definition for independence, or one way that we can prove independence, we have to see if a regular probability is the same as the conditional probability. So in this situation, we could look at the probability of having a data display and compare that and see if that's equal to the probability of having a data display given that the page also has an equation. Okay? That's our test for independence. We want to see, does having an equation change this probability of having a data display at all? And so our question is, are these equal? Or in other words, close enough, within that 5% that we talked about. All right, so going back to that chart, what is the probability of having a data display? Go back and look at that table or your Venn diagram that we made on the earlier page. And the probability of having a data display was 0.48. And so we're trying to see now, is that equal to this conditional probability? Well, how do we find that? The probability of data display given equation? We can use our formula for conditional probability that says this right here, this whole thing is equal to the probability of data display and equation all out of probability of equation, right? Okay? That's the formula for conditional probability. So probability, looking at our table again, that we have a data display and an equation on a page, that's having both. That's that 7%. But then we need just the probability of having an equation, and the probability of just having an equation, looking, is 0.27. So are those two equal? Remember, if they are, they're independent. If not, they're not. So compute that 0.07 divided by 0.27, and you should find that, no, they are not the same. 0.07 divided by 0.27 is approximately 0.26. Okay? So they are not the same, so therefore, they are not independent. Okay? Not independent. It appears that having the equation on the page made you less likely to have a data display, okay, versus just the probability of having a data display. Okay, we could have also done that the other way around and looked at the probability of having an equation and seeing if that was equal to the probability of having an equation given there was a data display. So looking for that. And if you want to, go ahead and calculate those two just to make sure you know you were doing what you're doing. You can hit pause and do that. Then when you come back to check, you should see that you get that, again, these are not equal. So it verifies this claim we made right there, that they are not independent. Okay? All right, so now, drawing without replacement, we're bringing that up again just to kind of remind you what that is. We talked about it in the last chapter. That's when you're doing something, you're drawing something out of a set, but then you're not putting it back in before you do the next draw. Okay? So I want you to try these. Please hit pause, try these on your own, and then when you bring it back up, all the answers will be there, and you can check your answers and see what you did. You might need to look up on the internet what a card deck consists of. I found that in recent years. Some of my students don't know the makeup of a deck of cards, so look that up on the internet if you need to, and then see if you can answer these questions. Okay? Hit pause and do that. All right, take a minute there and check your answers. Hit pause if you need a moment because I'm going to go ahead and move on to the next page. All right, so tree diagrams. Okay, just kind of hitting a bunch of different things here on this video. A tree diagram is a nice way to display probabilities when you have conditional probabilities. Shows the condition and then the probability of the event that follows the first event. Okay? So let's say we have this unofficial study done by the administration states that 73% of Hickman High School students stay on campus for lunch. Of the students that stay on campus, 58% are gold card holders. Of the students who leave campus for lunch, 32% are gold card holders. Make a tree diagram to represent this information. And again, this maybe might be something you saw in middle school, learning how to make tree diagrams. But if not, you basically show your choices for your first event. You can be on campus or off campus. And then we put the probabilities on the branches. So 73% stay on, which then we can do the complement then to say that that must mean 27% go off. Okay? Of those that stay on, we could be a gold card holder or not a gold card holder. Okay? Of the students that stay on, 58% are gold card holders. Then using our complement rule, that means 42% would not be gold card holders. Of the students that eat off, you could be a gold card holder or not, right? Those are two choices. So according to our problem, 32% are gold card holders. That means 68% are not. So there's your tree diagram. Okay, so it just organizes things nicely. So then doing these probabilities, what's the probability that a student selected at random eats on campus and is not a gold card holder? So we're doing probability of on and not a gold card holder. This is an and problem, and because we've organized these by the different branches, we've got the conditional probabilities on these second branches here, right? Those are the conditional probabilities. So when we use our rule, that's taken care of, right? Because these are dependent events. They're not independent. So if we're actually applying the formula, we need the probability of on times the probability of being a gold card holder, or not a gold card holder, given that you eat on campus. And these tree branches have already done that for us. So the probability of eating on campus is 73% times the probability that you're not a gold card holder given that you eat on campus. Well, that's what this is right here, because given we've eaten on campus, this now is the probability that we're not a gold card holder. So that gave us that conditional probability. So you multiply that out, and you should get approximately 0.3066, I believe. Okay? Go ahead and hit pause, and I want you to try the second one by yourself. All right, when you do this one, you should get the probability of eating off campus and not being a gold card holder is 0.27 times 0.68, which is 1836. Okay? Next one, what's the probability that a student selected at random is a gold card holder? Okay, so now we're just looking at the probability of being a gold card holder. All right? So there's different ways that can happen, right? You could eat on campus and be a gold card holder. So it could be these people. Or you could eat off campus and be a gold card holder, right? These or the red or the green, right? So using our rules, then we know we can do probability of on and gold card holder means we multiply by 0.58, or, so that's a plus, eating off campus and being a gold card holder. Okay? Compute those, and you should get approximately 0.5098. All right? What is the sample space? What are all our possible events here? Well, you just go down the branches. They're all organized nicely. So we could be on and a gold card. We could be on and not a gold card. We could be off and a gold card, off and not a gold card. So there's our sample space. Okay? So let's find out the probabilities of each of these events happening. Okay? You should assume that they're not equally likely to occur. And then what do you think we will get? Let's go ahead and find out. So let's find all these probabilities. I'm going to write them off to the side out here. The probability of being on campus and a gold card holder would be multiplying these two numbers together, right? And when you do that, you get 0.4234. For on campus and not a gold card holder, you would get this number. For off campus and gold card holder, we get that. And for off campus, not a gold card holder, I believe you get this. Go ahead and take your calculator and add those up and see what you get, or if you get what you expected. All right, that's the end of this video. I will see you in class next time. Remember, if there's anything in these videos that seems confusing, please mark it on your notes and bring it next time, and we'll talk about it in class, along with doing a bunch of problems. Okay? It's Friday. It's 6:30. I'm out of here. Hope you had a great weekend, and see you next week.